Good evening, everyone. Myself Yashvi Sheth, and today I will be taking the fifth live session for the course Basic Principles and Calculations in Chemical Engineering, taught by Professor Subrata Majumdar from IIT Guwahati. So, starting with this session, starting with the brief of the lectures taken by the professor. Uh, the lecture highlights some very important diagrams and terminologies. First one highlighted was the phase diagram. So what does a phase diagram means? Uh, so any material or any substance can exist in various states. It can be solid, it can be liquid, or it can be gas, or there can be a mixture of two as well. For example, if you have water and if you keep it in a deep freezer to solidify it, so there will not be some sudden transformation of water into ice. So there will be a intermediate transition. Firstly, there will be temp water which will cool down, which will cool. So its temperature decreases. So we will have cool water. Now there will be a certain point where there will be no temperature change, and this at this point there will be formation of conversion of liquid water into solid water. So there will be a dual phase water in liquid plus solid. So this is the transition phase, and after some point there will be again solid. Now, if you further keep on reducing the temperatures, again the temperature of that solid will change. Now, again the temperature will change. So, such type of transition can be between solid liquid or liquid to solid. It can be solid to gas or gas to solid, or it can be between liquid and gas. So such type of transformations like it depends on both temperature as well as pressure. Pressure plays a major role when you take into account liquid and gas, because the effect of pressure on solid is very less. Okay. So such type of relation on how the transformation between any of this phase occurs is shown by phase diagram, which is the plot between pressure and temperature. Okay, so here I just gave the example for temperature. It can be also like if you keep here you need to take into consideration that pressure is constant. So if you keep temperature constant, and there can be some relation between pressure as well. So this type of diagram shows how any material can be transformed into one phase to another phase. Say for example, you have, let's take the example of water only. So you have water in solid at this point. So this is the region where it has liquid phase, because it will just have liquid. Okay, this point, let's say A, it will just have liquid. Now if you keep the pressure constant at this point, and if you cool down, like if you cool down, if you go in this direction, then it will form solid. Now this solidification, there will be a transition. Now this is the transition line for solid and liquid phases. So at this point, if you take, then this point will have both solid and liquid. Now if you similarly, if you increase the temperature, then there will be transition of liquid to gas. Firstly the temperature, there will be some temperature rise, then there is this region is known as transition region, where liquid and both gas will be occurring and simultaneously. And later, if you further keep on increasing the temperature, then gas will appear. Just a second. So again, if you consider solid and liquid transitions, then conversion of liquid to solid is freezing or solidification, or solid to liquid is melting or liquefaction. Now, there can be certain examples where you have direct transition from solid to gas. Okay, so this is the transition line, and solid to gas transition is known as sublimation. So if for any change in pressure or temperature, you can directly convert solid into gas or vice versa. And for conversion of liquid into gas, it is known as vaporization. And for gas to liquid, it is known as condensation, because you are forming liquid droplets. So all these black lines are nothing but the transition line. Now, if you see, then there is one point where all the lines intersect. Now, what does this intersection mean? Now, intersection means all the phases, they exist together. So all phases are simultaneously present. And such a point where all the transition, like all the lines meet, is known as triple point. So you will have all gas, or like in gaseous state, in liquid state, and in solid state. Now another terminology which you come across in your upcoming classes, it will be vapor liquid equilibrium. So equilibrium is the terminology which was discussed in the class. It can be any equilibrium, like chemical equilibrium, where the concentrations, they become steady after a point of time because there is no further change in concentration. Or it can be thermal equilibrium, where the net transfer of heat between any two phases is constant. So here is one more type of equilibrium that was discussed, which is vapor liquid equilibrium. So it is known as VLE also, VLE diagrams, because the transition, these diagrams show how liquid to gas or gas to liquid uh, transition occurs when you have a mixture. So this phase diagram is all about pure component. So if you have a liquid, like if you have a mixture, then what is the type of transition that occurs? Okay, so here I told you that if you have any liquid, then firstly, if you, in liquid state, firstly if you keep adding heat, then what happens? Its temperature increases. That is because of its capacity to store some amount of heat. So there will be some rise in temperature. Still it will be in liquid phase. Now after certain point, there will be no change in temperature, as I discussed here, no change in temperature, and still you apply heat. So that heat will be consumed for the transition of liquid to gas, and there will be some liquid plus gas mixture at constant temperature T. Now again, if you keep on increasing the temperature, then all the liquid will get converted into gas, and further increase in further supply of heat will result into temperature increase and form gas, or it can further increase the temperature. Now this is for pure liquid. Now if you have two components, or two components in a mixture of liquid, then both will have different boiling points. Okay, so there is the chance that one of the liquid will start boiling first, and another liquid will boil later, depending on the boiling point. And now this boiling points or will also change, because suppose the liquid has interaction of type AA, and another liquid has type of interaction BB. So if you mix both of them, the type of interaction between A and B, that is the molecular force between A and B will change, and that is how the boiling point will also change, or the mixture will, that will, so there will be a region when uh, firstly A will start boiling, then B will start boiling, and there will be one section where A and B both will be vaporizing and all gets vaporized later. So there will be a region where boiling occurs, unlike the case where it is just a dot in pure component. So for that, this is the VLE diagram for which you plot concentration versus temperature plot. So here you have concentration of any component A, which is represented in mole fraction. And say for example, this is the boiling point, like this is the temperature at which it boils. Okay. So if it is pure mole fraction of A is 0 here, then total amount is 100%, it is B. And what is the boiling point of B here? Then this represents the boiling point. Now similarly, this is 100% A, so this is boiling point of A. Now in any other region where you have mixture, like mole fraction changes, so here suppose you have this as the starting point. This is the amount of A present, which is XA equals to 0.4, XB equals to 0.6. Now if you start increasing the temperature, then as I said, there will be some increase in the temperature of the system. Now this will depend on what is the specific heat of each of the component. Depending on that, that much amount of temperature rise will be observed. So once you, this plot, the lower plot is known as the bubble point curve, because till this point whatever was there was entirely liquid. Okay, so this region is known as subcooled liquid because there is still you are observing rising temperature. So this curve represents when you observe first bubble, like first bubble is formed from the liquid. Okay, so after this point, the temperature change will not be much. Okay, so if you so for this will represent vapor plus liquid. Okay, so this is totally liquid, this is vapor plus liquid. Now if you further keep on increasing the temperature, if you go in this direction, okay, so there will be continuously vaporization of liquid. Now here there is no dot because the boiling point is the range. So this is known as the bubble point because the first bubble appeared here. Now this is the curve which is known as dew point curve. Why it is known as dew point curve? Because the last dew or the last droplet of water disappears here, or we can say that all of the liquid is converted into its vapor form. So this region will be vapor form, and it is also the region which is known as superheated vapor. Like if you further increase the temperature of vapor increases. Now this line is known as tie line. Okay, so this represents the mole fraction of liquid phase, and this represents the mole fraction of vapor phase. So for that, what you need to do, if you are given any temperature and one of the mole fraction, then for that temperature, what will be the mole fraction of that component in vapor phase? You just draw a horizontal line, and the one where it intersects, it represents the mole fraction in vapor phase. So here this is nothing but vapor liquid equilibrium. Now for any temperature T, every liquid has some amount of vapor, may it be mixture or may it be pure form, it has some amount of vapor in a closed system. So uh, uh, that pressure is known as partial pressure in that system. And if it is saturated, like there will be no further change, then it is known as saturation pressure, because further and saturation pressure is nothing but it represents the pressure which is exerted at the boiling point. So about uh, higher pressure for that particular temperature cannot be expected. So to find out what amount of pressure in the vapor form can be exerted by a liquid at the boiling point is known as saturation pressure, and it is calculated by this equation called Antoine's equation. And here A, B, C are constants which you can get from any of the appendix of chemical engineering book. Moving forward, the next lecture talked about various terminologies which are also related to some equilibrium process. Uh, so one such equilibrium law is nothing but Raoult's law. So it relates at equilibrium what is the partial pressure exerted by any component. Like say for example you have mixture A, B, and it is a closed system. Okay. So now there is both liquid and vapor. So all this is all about equilibrium process. So there are various laws which represent equilibrium process, and to find out various process variables based on that equilibrium condition. So there is one law: if you have liquid and vapor system with multiple components. Now I said that if you have pure liquid, there will be a certain type of interaction. Say for example it is AA bond. Now for B it will be BB. So if you mix both of them, the interaction will be of type AB also present in the mixture. So it can be, so the bond between A and B, it can be same as AA and AB also, or it can be either weak bond or it can be strong as well. So now this bond depends on the type of interaction, like if they are uh, like compounds, if you mix water and milk, so they are easily miscible, and so depending on what type of mixture you have, then the bond will depend on that. Now if you mix oil and water, then what will happen? The interaction will be very weak as compared to the pure components. So what will be the partial pressure, or what will be the pressure due to each component? This is obtained from Raoult's law, and it states that the pressure that is exerted by any of the component A or B, it is related to the mole fraction of that liquid. Okay, in the liquid, mole fraction of that component in the liquid phase, which is represented by Xi. Now this is the partial pressure which is which can be written as YIP as per Dalton's law, and which is nothing but equal to Xi Pi set. Now Pi set is nothing but the pressure or the vapor pressure of any liquid, pure liquid, which is exerted in a closed system at its boiling point, which was calculated by Antoine's equation. Okay. Or here if you want to calculate even normal pressure at any other temperature, it will be ln only. So yeah, so here there is one assumption that, as I mentioned here, the bond between A and B, it can be weaker or stronger as compared to the pure liquids. So here we assume that the bond between A and B is equivalent to the bond, or it is similar to what bonds were present between pure A molecules and pure B molecules. So in that case, the liquid or the mixture is said to be ideal in nature. So this law is applicable only for ideal mixtures. Now, if you have some different type of interaction between A and B, then you need to take into account some real, which is nothing but non-ideal mixture or real mixture. Then you need to take into account what type of interaction exists. And for that, there is one constant gamma, which is nothing but activity coefficients that represent the type of bond between any two. So this is all about what type of equilibrium it can exist when you keep any mixture of liquid in a closed system. What will be the mole fraction or what will be the composition in each of the phase. Now relative volatility. This is the another terminology which is used for vapor liquid equilibrium. Okay, so this is very important if you talk about the application in distillation column, where you feed any liquid or maybe liquid vapor mixture. Now this liquid is boiled, and depending on the difference in the boiling point, the one which boils faster, it moves upward and it is collected at the top, and another which is less boiling, it is collected at the bottom. Okay, so now the height of this column, it depends on the difference in the boiling points, because if the boiling point difference is more, then you need to give more amount of space so that both the components are separating out. So there is one terminology which is used to differentiate or used to show what is the difference or what kind of difference is observed in the volatility or the boiling points of two components, which you need to separate by boiling point difference. So relative volatility, as the name suggests, it represents what is the difference between the volatility of two components, and volatility is represented nothing but by boiling points. So for that, alpha AB, as it is written here, it is nothing but the ratio of partial pressure of A divided by its mole fraction divided by PB by XB. Now this can be written as YA by P into XA. This is total pressure, YB by P XB. So this pressure will get cancelled. Now this will be YA by XA upon YB by XB. Now, as I have mentioned earlier, the system can be ideal or it can be real. Or now if you consider ideal case here, then Y by X, like P gets cancelled out. So in that case, Y by X is nothing but saturation pressure. So PA set by PB set. So which is nothing but the ratio of saturation pressure of each component. So if you have a real system or non-ideal components, then in that case, there will be a gamma, which is nothing but the activity coefficient. It will appear here, gamma A, gamma B. Another terminology which was highlighted was which is also a vapor liquid equilibrium. It is used for sparingly soluble gases in liquid. So this is represented by Henry's law, where you relate the partial pressure of gas in the with the mole fraction in liquid phase. One of the best example of partially soluble or sparingly soluble gas in liquid is nothing but carbon dioxide. These carbonated drinks or any soft drink we drink. So in which carbon dioxide is dissolved in the liquid. Okay, so which is in very less quantity. So what is the amount of pressure that it will exert? So that Pi is related as X, which is the mole fraction in liquid phase, into the Henry's constant. So this moving forward, there were some new terminologies which is related to uh, the most commonly used, which is humidity. Humidity is related to what amount of air is present in water. Okay, so it is a measure of amount of water present in air. So there are some terminologies which are related to humidity, which is also a kind of vapor liquid equilibrium, where water in air is in equilibrium. So dry bulb temperature, it is nothing but the temperature which is prevalent of air, like at normal stage if you measure the temperature with any thermometer. So it is any temperature measured with thermometer of air. Now it will have some amount of water. Okay, now if you observe, then if you stay near some ocean, or in areas like Mumbai coastal region, or if you stay in some dry region away from some coastal lines or so, then there will be difference in the humidity. So if you stay in Mumbai, then what will you feel? At the same temperature also, there will be the air, you what you say, the air is very humid. Okay, and what does that mean? The amount of water in that air is more, because the vaporization of water from the nearby ocean, it is more as compared to the dry regions. So in that case, air has some capacity to store water in it, which is nothing but represented by wet bulb temperature and dew point temperature. So wet bulb temperature is nothing but uh, it is a kind of saturation point where uh, the chances of air able to uh, the chances of water carrying capacity of air is no more, so which is nothing but saturation. So for that, what you do, you take a thermometer, you wet wet a wet the bulb of thermometer by putting wet cotton on its surface, and then you allow to get equilibrium. So what will happen? The temperature will reduce, and that temperature is nothing but wet bulb temperature. Another point, another as I mentioned, is dew point temperature, which is also kind of saturation, which is also saturation temperature, because like if you have any air, if you keep on, like, air will have some capacity to carry some amount of water. Now if you keep on adding water, then the temperature will reduce, and also what will happen, dew point temperature represents where first droplet of water comes out of air, so which is nothing but dew point temperature. And above this is also called as saturation point, because below this point, at this temperature, the air is no longer air will no longer be able to store carry water. So regarding this temperatures and terminologies, further discussion was made in lecture 15, where as I mentioned, humidity was talked. Humidity is nothing but the amount of water carried by air, which is carried by 1 kg of dry air, so which is nothing but moles kg of water per kg of dry air. So it can be calculated by, now since for vapor phase or for gaseous phase, it is better easier to calculate in pressure, and also pressure is kind of concentration. So what we do, PA is nothing but the partial pressure of water at the temperature. So humidity is nothing but PA by what will be for dry air? It will be nothing but total pressure minus partial pressure of A. So this is in terms of pressure. Now, if you want to convert in kg of water per kg of dry air, then for that, what you need to do, you need to multiply by the molecular weights, which is nothing but 18 by 29 if we round off PA by P minus PA, which will be kg of water per kg dry air. Now, relative humidity, it is nothing but what is the maximum uh, storing capacity of water in air and what is the actually it is present. So what is the difference between two? So this is nothing but partial pressure of water in present situation. And what is the amount of maximum air that can be stored? It will be nothing but equal to the saturation pressure of water in at that temperature, because at that temperature saturation pressure is the maximum amount of pressure that water can exert. So it is nothing but saturation pressure or P set. So depending on that, the terms which I discussed in previous slide, dry bulb temperature, wet bulb temperature, dew point, relative humidity, and there are many more terminologies like specific humidity, specific volume, uh, enthalpy, etc., which is calculated from chart. Okay, and this chart is known as psychometric chart. So here what is required is you just need two data points, and from that any other data points, relative humidity, dry bulb temperature, wet bulb temperature, dew point temperature, then humidity, specific volume, etc. Like enthalpy also, enthalpy of that air, etc. can be calculated. So, for example, if you are given with uh, 30 degrees of air which is having dew point of, so all these lines are dew point lines. So here you will be given some values of that dew point. So this is the dew point value. So if this we stretch, and if we stretch this line, then this is the interaction point. So all these lines are nothing but relative humidity lines. So if you draw one such line here, and the one the percentage which shows here, it will be relative humidity. If you stretch this point to this side, then what you will get is specific humidity, or humidity in kg per kg of dry air. Then there is if you want to find wet bulb temperature also, then you can find. So likewise, you can also like specific volume, like what is the volume of water per kg of dry air. So all these lines are of specific volume. So at this point, you draw one such line and you find out the value. So this is how you read a psychometric chart. So any 2 points will be given, and based on what interaction point, you just stretch what you want to find out along that line, and you will get the value. Now moving to the assignment part. Uh, First question given here is, by Gibbs phase rule, the number of components degrees of freedom and phase are related as dash. So if we want to derive Gibbs phase rule, if we want to derive degrees of freedom by Gibbs phase rule, what you will do, say for example, you have any system with let's say p amount of phases. Okay, so and each phases will have some amount of equilibrium because there will be some amount of interaction between any phase, P1 phase with P2 phase, P2 with P3, P3 with P1, and so on. So there will be interaction of each of this phase, and each phase has n components. Here it is mentioned as C. So let's say it has, each component has C, each phase has C components. Okay, and each phase will have at equilibrium the temperature and pressure are the variables which will be constant. So what you will have is for components, the number of variables that you will have is C minus 1, because let's say you have three components and mole fraction in each mole fraction then for each phase you can write x1 like for first phase you can write x1 plus x2 plus x3 equals to 1. Then there will be some relation for x1 and x2, and from that another third one can be calculated easily. So for each phase you can write such variables. So x1, x2, x3 you can get, and for each phase, so it will be number of phases multiplied by C minus 1, plus there will be two more variables which is temperature and pressure, which is added over here. Now there will be some amount of constraints or some amount of values that you will get from if you have equilibrium relationships. So such relationships, if you have, say for example, if you take vapor liquid equilibrium and you have two phases, vapor and equilibrium, vapor and liquid, then in that case what you will get, you will get one equation from Raoult's law, xi pi set. So how much such relationships or such equations help you find out more and more variables. So how many equilibrium conditions you will have, it will be nothing but it will be dependent on condition and phase as this. So what degree of freedom you have with you, or what you can choose independently, degrees of freedom will be nothing but P into C minus 1 plus 2 minus C into P minus 1. So it will be nothing but PC minus P plus 2 minus PC plus 1, sorry, plus C. So it will be 2 minus P plus C. It will be nothing but F. So the correct option here is, if you change it, then it will be nothing but P plus F minus C equals to 2. Moving forward to the next question. So it is asking here is degree of freedom for triple point is, so what is the formula for degree of freedom? F equals to phases minus number of phases plus number of components. Okay. So at triple point, it is the main point to be considered here in this question. So at triple point, number of phases will be 3, which is solid, liquid, and gas. Okay. So triple point has three number of phases, 2 minus 3 plus number of components. So here it is not mentioned, but triple point means you are considering single component. So component here is 1. So there is no mixture. So which is nothing but 2 minus 3 plus 1, which is 0. So at triple point, the degree of freedom that you have is 0. Next question is, which of the following is wrong about the phase diagram? So this is the phase diagram which I talked about earlier also. If you look at the options, then it gives information on the transformation rates. Relative amount of different phases can be found under a given equilibrium condition. So if you look at all the options, then transformation rate, like at what rate one phase will be converted into another phase, that cannot be obtained. But if you look into this option, relative amount of different phases can be obtained. So this can definitely be obtained, because you can say whether it is pure solid or pure liquid depending on the condition. It indicates the temperature at which different phases start to melt. Yeah, obviously, because uh, this region shows from which melting will start. So this is obviously obtained from this graph. And another is solid solubility limit can be depicted. So if you have this point, okay, so this will have certain amount of solid XS and XL. So what amount of solid it will be bounded at this point. So that can also be limited, and that amount of solid, like it is the, since it is the maximum amount of solid, it is also known as the solid solubility limit. So the answer which is not matching here is, it gives the information on transformation rates. So option A is correct. This is the same question. So let's not go into that. Next question. When the system contains one phase and 2 degrees of freedom, it is called as, so for a system which has 2 degrees of freedom and one phase, it is called as bivariant system. Moving forward to the next question. When air reached its dew point, then what is the case? So I have clearly talked about what dew point is. So air has some amount of carrying capacity. So depending on the water carrying capacity, air can be unsaturated and air can be saturated. Now this saturation point is denoted by dew point. So here the correct answer is dew point, because as I have explained earlier, dew point represents the maximum water carrying capacity of air, because if you further add water into like if further water evaporates and adds into air, then water will start forming dews. So it is, the correct answer is, it is saturated. The vapor pressure is related to the enthalpy of vaporization in following equation. So if we look into each of the correlationships, then Dalton's law, it relates partial pressure with the total pressure in a gas mixture. Then another is Clausius-Clapeyron equation, which talks about the relation, like which is this relation. So it gives the interdependence of pressure and temperature along the phase equilibrium curve of a pure substance, and it relates like pressure and temperature are related with heat of vaporization, because it is nothing but equilibrium process. Okay, So this is the relation. So this is the correct answer. If we look into what another equations are, we should look into. So Maxwell's equation is the set of equations which gives you relationships between enthalpy, internal energy with temperature, pressure, and etc. So it shows interrelationships. Now, Raoult's law I have explained earlier in this lecture also. Raoult's law relates partial pressure Pi with the mole fraction of that component in liquid phase. So this is also not the answer. So answer is B here. Moving forward to the next question. Negative deviation from Raoult's law mean dash. So negative for that I have mentioned that Raoult's law is suitable for ideal mixture where you have similar type of interaction existing between two molecules A and B as in the case of pure. So I had also mentioned that this type of interaction between A and B, it can be weak interaction also as compared to both AA and AB, or it can be stronger also. Now, depending on the type of interaction, now if it has weaker interaction, then the mixture will boil faster and the pressure exerted will be more as compared to the one which will be exerted by pure components. So this is the one which has like it is nothing but known as positive deviation where you observe weak interaction from the one which was in the original case in the case of pure components. So this kind of behavior is known as deviation from ideality. So depending on the type of interaction, so if it has weak interaction, it is known as positive deviation where you have the pressure of the total system or vapor pressure of each components are found to be higher than what is exerted by pure component. So in mixture you will have higher pressures. Now this is nothing but positive deviation. Now if system has stronger interaction, then what will happen? The interaction, since it is stronger, then you will have to apply more amount of energy, more amount of heat to boil that uh, uh, boil that uh, mixture. In that case, the pressure at any temperature will be lesser as compared to what it was exerted in the case of pure system. So here the pressure is lower and this type of behavior is known as negative deviation from Raoult's law. This is nothing but negative deviation and it has stronger interaction. So the correct answer here is negative deviation from Raoult's law mean vapor pressure is lesser. Moving forward, for binary mixture at a constant temperature, the relative volatility dash. So for that, if you like as I mentioned, relative volatility is nothing but it shows it is the ratio of PA set and PB set, and these are nothing but the saturation pressure at boiling point. Okay, so now here the temperature is constant, but you are increasing or you are changing the pressure. Okay, so say for example, if you increase the pressure, now if you increase the pressure, the boiling point tends to increase, and this is the trend which is followed. Now in the mixture there will be one A, low boiling, and B, which is high boiling. Okay, so if you increase certain amount of pressure, okay, so if you increase, let's say this is P1 and this is P2, then the change in boiling point for this component is this much, and for another this is the T1 and T2 boiling point for component 1, TA1 and TA2. And say for example, the boiling point uh, like for component B, then there will be the change in boiling point will be less, because the here the change will be more, and for higher boiling case, for same change in pressure, the boiling the change in boiling point will be less. So similar effect will be observed in PS set and PB set. So since alpha is nothing but the difference in the boiling point, so as you increase the pressure, the difference in the boiling points, it reduces. Reduces. So what can you say that a decrease in relative volatility, it decreases with increase in total pressure. And if it should not increase with decrease in total pressure, which is wrong. It is also not constant, and it does not increase with increase in pressure. So correct answer is A. Next question is, the solubility of gas in water depends on dash. So the gas the solubility of gas in any solvent or in water depends on temperature also, pressure also, nature of gas also. So all of the above. So reason for that is, say for example, if you have aerated drink, so carbon dioxide is dissolved in it. So here you can say that the gas is soluble in in liquid at lower temperatures more, because its mobility will be lesser, so more amount can be solubilized. So now if you open the bottle of any drink, so what happens is, it immediately comes into contact with room temperature, and the pressure also is atmospheric pressure. So what happens is, it tries to attain equilibrium, and the gas carbon dioxide comes out of that system and it vaporizes. So it depends on temperature, it depends on the pressure also, because if you have a closed system and if you open it immediately, there will be a drastic change of pressure, and depending on change of pressure, the gas comes out. Also it depends on the nature of gas also, definitely, because uh, it it shows the type of interaction that will occur between gas and water. So the correct answer here is all of the above. Moving forward, calculate the mole fraction of carbon dioxide when dissolved in water at partial pressure 0.001 atmosphere and at room temperature, given Henry's constant as this. So Henry's for this you need to use Henry's law, which was discussed earlier, which is nothing but partial pressure equals to X mole fraction into Henry's constant. So if you just put up the values here, you need to find out mole fraction X, which is nothing but X equals to P by H. So if you put up the values, correct answer is, it will come out to be 1.72 10 raised to minus 7. Okay, so that is the correct answer. Moving forward, heating of a liquid at constant pressure, it will result into vaporization. Now, if the rate of water evaporation is 0, then the relative humidity of air is dash. So what happens is, if you have air and if it has some amount of water vapor, say for example its relative humidity is, let's say, 15%. So it still can accommodate 85% more. It is still 85% unsaturated, and that much amount of water can be still added. So there will be some amount of evaporation, and that rate of evaporation will depend on what amount of water can be further stored and what is the amount of water which is actually available nearby. So it has further storing capacity. It depends on the saturation. So now if you have relative like the rate of evaporation is 0, so as I said, if it has some amount of vapor still to be uh, added in air, it still can accommodate some amount of water, then water will continuously evaporate and it will be added into air. So when it will stop, the rate of addition of water, it will be more when the difference, like the relative humidity, is less. So this rate of addition, rate of water evaporation, it will reduce when the difference reduces, or when it has more and more amount of water in it, and further it will not allow any of water, like addition of water. So there will be a net change, like there will be some amount of water getting condensed also. So it is an equilibrium process. There will be some amount of vaporization. So if air is unsaturated, the rate of vaporization will be more, and so water content can be still increased. And at there will be some point where there will be this equilibrium, rate of condensation and rate of vaporization or evaporation, you can say, will be equal, and that is known as rate of evaporation is 0, like net rate is 0, because the whatever is getting evaporated, same it is getting consumed, so net rate is 0. So it occurs when the air is saturated, so at that point relative humidity is said to be 100%. Moving forward to the next question, when dew point temperature is less than wet bulb temperature, then air is said to be, obviously it will be unsaturated, because dew point temperature represents the one, like further if you still try to add water in air, air, then what will happen, it will start forming water droplets. So if this is less, then what does that mean, still at this temperature there is still some amount of water carrying capacity of air remaining, which is nothing but air is unsaturated. Moving forward to the next question, in a psychometric chart, moisture content lines are, so I have shown you the psychometric chart, and it is represented by the it was represented by the vertical axis on the like y axis on the right hand side, which was nothing but specific humidity line, which gives you humidity in kg of water per kg dry air. Okay, moving forward, in psychometric chart and at any point in saturation curve, dry bulb temperature is always, so dry at saturation curve. So since air is said to be saturated, then dry bulb temperature, it can be same as corresponding wet bulb temperature. Okay, since wet bulb temperature is also a kind of saturation temperature. Now natural phenomena like fog and mist are due to what? So these are nothing, fog and mist are nothing but water droplets in air. So this is nothing but if you reduce the temperature of air, then as I said, there will be some amount of water, like since dew point temperature is crossed, there will be some amount of condensation of water. So like conversion of water vapor into liquid phase, which is nothing but observed in the form of droplets. So this conversion is nothing but known as condensation. So the correct answer is condensation here. So next question is vaporization begins at, for this question, I had said that triple point is the one where all the uh, three phases exist, which is solid, liquid and gas. And dew point is the temperature where last dew or last droplet disappears. So the correct answer here is bubble point, because this is the point where first bubble appears during like if we increase temperature, and which is nothing but vaporization of liquid. So correct answer is bubble point here. Next question is, if the concentration of CO2 dissolved in sparkling water in a closed soda can is this. So concentration is here given in 0.75 mole per meter cube, and find out the partial pressure of CO2 P. CO2 you need to find out, which is like in bar at this temperature. Henry's constant is given as this. So for this question, what you will do, there is one more correlation which is also represented by Henry's law, where you have some where there is some different units used. So here the concentration of gas in liquid phase is related to partial pressure as C equals to H into P. So if you use this correlation and if you put up the values, then partial pressure of CO2 will be nothing but concentration divided by Henry's constant. And if you put up the values, the correct answer will come out to be 2.2 bars. Next question is, air water vapor mixture has a dry bulb temperature of 60 degrees Celsius and a dew point temperature of 40 degrees Celsius. Then the total pressure is 101.3 kilopascal, which is total pressure is for what? Air plus water. And the vapor pressure of water at this temperatures will be, so this will be the partial pressures at that temperature of water. So what is the relative humidity? So relative humidity is always in terms of percentage, but here if you look into the options, it is mentioned as kg of water per kg of dry air. So how will you do this, solve this question? So this is nothing but humidity. So if you want to find out the humidity, what is it? In terms of kg of water per kg of dry air, it is nothing but 18/29 partial pressure of water per pressure of dry air. So what will be the partial pressure in this case? Since you need to find out the humidity, which is not saturated air, so the pressure correct will be related to the dry bulb temperature. So if you put up the value 18/29, 19.91 divided by 101.3 minus 19.91. So it will come out to be 0.152. Now again, if you want to find out relative humidity, so in that case, what you will do, relative humidity is nothing but the saturation pressure divided by partial pressure. So saturation will be at 7.3 divided by 19.9, which is the partial pressure here. So it will be uh, it will be nothing but 7.3 divided by 19.9, which is 36%. 36%, 0.6% saturated, which is the relative humidity. So it contains only 36 percentage of water as compared to what it can store. So that's all for today. So if you don't have any doubt, I will end this session. Thank you, everyone. Thank you.